Right. So this is our last class of the year, and we started looking at the different kinds of plate boundaries last class. So just a quick review. We have this nice map showing the major plates. And we talked about the three types of boundaries down here at the bottom of this slide: diverging, converging, transform. Think to yourself, what do those mean? What is diverging? Did we just diverge when we came together here? Actually, no, we converged. So diverge is when things go apart, converge, they come together. Transform means they slide past each other. They don't crash into one another. They don't move apart either. It's kind of like on a freeway where there's one car going one way and another car going the other way. They just slide past each other. That would be transform. So three kinds of boundaries, but there are two different things with converging boundaries, two different kinds of converging boundaries we have to look at. One of them we looked at last time. The other one we'll look at today. Then we compared the two types of crust, and we filled out this chart comparing the different types of rock, the thickness, the density, and the age of each of these types of crust, right? So at a diverging boundary where the plates are moving apart, correct? The magma comes up, it lifts up this mountain range. Remember, this is in 3 dimensions. It might look something like this. There's a valley at the top of the mountain range called a rift valley where the plates are being torn apart. And then everything gets dragged to the side. And as this occurs, this sea floor grows bigger and bigger because this whole thing is underwater. Usually, we can find it on land too. There's this place in Africa where this is happening. But this is a diverging boundary. Now, for each of these boundaries, I also wanted you to write down 3 things about them. I wanted you to write down features that are found there. So for this one, it would have been the mid-ocean ridge and the Rift Valley. I wanted you to write down processes that occur there. And in this case, it was seafloor spreading, where the seafloor grows bigger and bigger as it spreads apart. And then the final thing I wanted you to write down for each of these boundaries is some examples. Our best example for this one is the Mid-Atlantic Ridge that goes all the way from Iceland almost to Antarctica. Another example, though, is the Red Sea. And another example is the Rift Valley of Africa, where the African continent is getting torn apart. Okay, then we went on to look at one of the types of colliding boundaries. And this is where 2 continents collide. So a really good example of this was where India has collided with Asia. Really good example. And this formed the Himalayan mountains. And the feature that we find here is this folded mountain range.
I'm here, Mr. Fairley.
Well, it's about time, Rose.
Sorry.
Thank you for joining us. So we're just reviewing right now before we move forward. So that was good timing. At any rate, the Himalaya Mountains, the tallest mountains in the world, were formed by India colliding with Asia. Really good example of this first type of converging boundary. And the feature that's formed here is this folded mountain range where the land is crumpled up. And then, let's see, the process that occurs here is mountain formation, specifically mountain folding. That would be different than this example that we had for our mountains. Did I show you this already? Where we have these mountains rising up on either side of a fault and the lake basin in the middle dropping down below. That we call a fault block mountain, different than these folded mountains. So these guys are kind of like if you were to slide two carpets towards each other, they'd crumple up. So that was our first converging boundary, but we have a second one as well. So that's where we're going to pick up today, is with converging boundary type 2. So we're going to start by putting a new title at the top of another piece of paper. I would suggest make this about half the paper in height. And we're going to label a whole bunch of things here. So go ahead, converging boundaries 2, and then draw that basic start to the diagram. So this is going to have the process of subduction. And I want to remind you. Sorry?
I don't think Marisol can hear you.
You can't hear me?
Marisol. She texted me. She said she can't hear you.
Well, if you guys can hear me, then it must be on Marisol's side. Let me see. Maybe her speakers are turned off. Okay, thanks for letting me know about that, guys. Okay, so we need the title at the top that says Converging Boundaries 2 Subduction. So two kinds of colliding boundaries. This one is really interesting. So let's start by showing that we are having the ocean floor colliding with a continent. And so I'm going to draw the ocean in there. So I want to remind you that the ocean floor is made of a rock that we call basalt. And the basalt we symbolize with these stripes. Meanwhile, the continent is made of granite, which we're going to show with these angled lines, kind of like a letter X, except they don't cross. Hey, Noah. Can you hear me?
Yeah, what's up?
You can hear me? Okay, huh?
Yeah.
Okay, thank you.
Yeah.
Okay, so these are are two plates, one an ocean plate and one a continental plate being carried together. And the one we looked at before was a continent versus a continent. So you might wonder, what about an ocean versus an ocean? And with the two ocean plates colliding, pretty much the same thing will happen with them as with this boundary. So we don't have to worry about a separate boundary. All right. So what we're going to do is add our moving magma, because of course everything is caused by movements of the magma. The convection currents. Since it's very hot, I'm going to switch to red. So the ocean plate is moving towards the continental plate. Meanwhile, the continental plate is moving towards the ocean plate. So they are coming together. They are converging. And right here is where the convection current is cooling off and sinking back deeper into the mantle. So as usual, everything is driven by the convection current. Down here, when this plate gets pushed down in here, it's getting hotter and hotter. And so it starts to melt. This rock that used to be at the bottom of the ocean melts and forms fresh magma. Now, a lot of that magma is combined with the seawater that got dragged down with the plate. And as a result, the density ends up pretty low. And as you know, things with a low density rise upwards. So we're going to start seeing some of this magma pushing its way up through this continental rock. And eventually, some of it is going to erupt in a volcano. And this is why we have the ring of fire around the Pacific, because there are many subduction zones there. So what we're going to do with this diagram, because there's a lot of things going on, we're going to number different parts of it to describe what's happening. Okay, so let's start describing what's happening here. So we're going to make a key. So underneath, I'm going to write up here, right? But then I'm going to write number 1, then I'm going to erase it and write number 2. So you guys should write everything underneath the diagram. Make sure you have room for all 7 things. So down there at the bottom, step 1, convection currents are driving everything. They're the force that moves these plates. And the convection currents are dragging an oceanic plate towards the continental plate. So write that down underneath your diagram, and then I'm going to erase it, and I'll write down number 2. All right, how are we doing? Can you give me a thumbs up when you're done with that? Great. Okay, so I'm going to erase all of that. Step 2. So this one is going to have to do with the ocean plate getting pushed underneath the continental plate. And perhaps you remember that the cause of the one going underneath the other, the reason that the ocean plate goes under is because it's more dense. It's heavier material. So the denser oceanic plate is pushed and pulled under the lighter continental plate. So this oceanic plate is being pushed from a spreading center, from a diverging boundary by seafloor spreading. It's being pushed towards the continent. But then at the same time that it's being pushed, it's actually being pulled underneath because of the mass of the plate that's already gone underneath there. It keeps pulling more behind it. Now, number 3 is this whole area that I've circled. And this is where subduction is actually happening. So this is what we call a subduction zone. And as you can imagine, as one plate is sliding along underneath another, it's grinding along and they're uneven surfaces. There's these jagged projections that stick out, and sometimes they stick together, and the pressure builds up. And then when the pressure releases, we're going to have a big earthquake. And we can actually tell where a subduction zone is because the earthquakes form a line along the edge of the subduction zone and they get deeper and deeper. So what I'd like you to do is go back to your diagram and we're going to draw these stars along this subduction zone, right along the boundary between these two plates, to represent the earthquakes that occur as the plate gets dragged deeper and deeper. And of course, we have to put a key. So I'm going to do that down here since I have some room. All right, now when that plate gets deep enough, it's going to heat up until the rock that makes up the plate. And remember, this is like 5 miles thick. So this is a lot of rock that we're talking about. Once it gets hot enough, it's going to melt. So that molten rock, the melted rock, we call magma when it's still underground. Once it erupts out of the volcano onto the surface of the ground, then we call it lava. Magma and lava are the same thing. It's just that one is underground and one is on the surface. Now that we have this molten magma, it has a low density, so it's going to start to force its way up through the rocks of the crust above it. And this will actually cause earthquakes too. Probably not as big as the earthquakes caused by the two plates grinding past each other, but this does create more earthquakes. And of course, this is all very slow from our viewpoint. You know, the subducting plate might only move this far, just a few inches every year. Um, and then as the magma melts and rises up through the crust, it also might only move a few inches or a foot in a year. So it takes a long time for all of these events to occur, until the magma breaks through the surface and all the pressure is released and it explodes into a volcanic eruption. So this is where there's one little detail that's different between a continent and an ocean floor running into an ocean floor. Everything is the same, where one piece of ocean crust gets pushed underneath the other piece of ocean crust. But here, what we've drawn is a volcano that's on a continent, like Mount St. Helens or Mount Rainier or Mount Lassen or Mount Shasta in the Cascade Mountain Range that goes from Northern California up to British Columbia. On the other hand, if this happens where one ocean floor runs into another, then you get a volcanic island forming. And you don't just get one volcanic island, you get a whole chain of volcanic islands. Like Japan. That whole country of Japan is formed by subduction, making a bunch of volcanic islands. And so we call this a volcanic island arc, because normally they have a curved shape. So a volcanic island arc would be the alternative version of this if it was an ocean floor versus an ocean floor. Okay, so we either get these continental volcanoes or we get volcanic island arcs. That second one would be when two ocean crust plates collide. Now, the last thing that I haven't talked about yet is number 7. And number 7 is showing where the sea floor actually gets pulled down deeper and deeper and deeper. We get this long, narrow valley of underwater depth. And we call this a deep sea trench. And this is the deepest place in the world. One of these deep sea trenches is the Marianas Trench. Maybe you've heard of this before. It's the deepest part of the ocean. It's near the Philippine Islands. It's where the Philippine Plate is subducting with the Pacific Plate. And that deep sea trench, the Marianas Trench, is 7 miles deep. Now compare that to Mount Everest, tallest mountain in the world, 5 miles tall. So you could take Mount Everest and drop it into the Marianas Trench and you'd still have 2 miles of water on top of it. Really deep. So that's number 7, is this deep sea trench. So you can see that these plate boundaries explain a lot of Earth's surface and as well as different geologic events like earthquakes and volcanoes. Um, so give me a thumbs up when you're ready to go on. If you need me to repeat one of the numbers, let me know. Okay, looks good. So I'm going to erase everything here. We're going to go on to the next slide, okay? Okay, so the first part of this, you're not going to write all this down. Again, we're looking for three things. I want you to look for features that are formed at this boundary. I want you to look for the process that occurs there, and I want you to look for an example of, or a few examples of where these happen. Okay? So, just to review, convection currents in the asthenosphere, that's the lower mantle. These convection currents carry a continental plate towards an oceanic plate. The denser oceanic plate gets pushed under the lighter continental plate. As the oceanic plate drops, a deep sea trench is formed. As the oceanic crust gets pushed deeper, it heats up and melts into magma. The hot magma rises and pushes through the continent, eventually forming a volcano, or it pushes its way through another piece of ocean crust and makes a volcanic island arc. Earthquakes also occur along the subduction zone as one plate gets pushed under the other. Subduction is the process where one plate is pushed underneath another plate. Examples include Mount St. Helens, where the Juan de Fuca plate is subducting below the North American plate. Subduction also occurs where oceanic plates collide. Indonesia is an example. So remember, I wanted you to look for features, right? So let's start with some features that you should write down. Features found at a subduction boundary. That would include a deep sea trench. It would include a volcano or a volcanic island arc. Also, we have the subduction zone. That would be another feature. This is the place where subduction is happening. So we have three features to think about. So make a note that we get these three features. Maybe four. We also have earthquakes. Then I asked you to look for the process that occurs at this boundary. Well, this boundary is named for that process, right? Subduction is the process that we're looking for. I also asked you to look for examples. One famous example is Mount St. Helens. Or I know Gabe's interested in Mount Rainier. That's the same thing, formed the same way. The entire chain of mountains of the Cascade Mountain Range is an example. Another example would be Japan. Another one is Indonesia. Another is the Marianas Trench. Maybe you know the Aleutian Islands, part of Alaska. And they're a really good example of why we call it a volcanic island arc. If you look at the shape of Alaska, it's something like this. Drops way down over here. That's basically Alaska. And then this continues in a chain of islands that make this arc shape. So the Aleutian Islands of Alaska is another good example. All right. So you needed to write down, it looks like 4 features, a couple of examples, and the name of the process, subduction. Did you have a question? Okay. So write down the features, the process, the examples. And then give me a thumbs up. All right. Just in case you're wondering, In Alaska, this is how we spell the name of the islands. The Aleutian Islands, named after the Aleut people, native people that first lived there. All right, let's take a break from the writing and look at a video. Okay, so here we see the globe, and then it's going to put them all back into Pangea. They're going to move apart, C4 spreading occurring in the Atlantic. All those red lines were subduction zones. Here's a diverging boundary. You can see the material moving apart. That would be a mid-ocean ridge and a rift valley. On the left, we have a convergent boundary where we have a piece of oceanic crust going underneath another piece of oceanic crust. Now, these guys should have the same density, but the older the crust gets, the cooler it gets, and that causes it to become more dense. And that's why one piece of ocean crust would dive underneath another piece of ocean crust. On the other hand, if it's continental crust, it's obvious because it's less dense. And one way or another, we're going to get one plate sliding underneath another, like we see here. As it gets subducted underneath there, it's going to heat up and melt. And as it melts, that is going to form a volcano. Along the way, we also get this deep sea trench. They're showing that with the red line here, where the one plate is folded underneath another one. It's really deep right there. 7 miles in the case of the Marianas Trench. Sometimes they dive down underneath another plate at different angles. And sometimes somebody puts a person on their animation that I'm not sure why. Oh, because they're representing the process of slab pull, where basically the mass of the plate is pulling itself down. I like this one because it shows the direction that the Pacific is moving, and it shows why we have the ring of fire all along the edge of the Pacific plate. 10 centimeters a year, that's not quite a foot, it's maybe a little less than half a foot. That's the location of the Marianas Trench, deepest place in the world. Some sediments are dragged down with the plate, along with some seawater. And when all those things mix together and melt, it forms this lightweight, low-density magma that can rise to the surface and form a volcano. In this case, it's forming a volcanic island, but that magma can work its way all the way through a continent as well, and you get a full-on continental volcano. Okay, so analyze this diagram for yourself for a second. Let's start with this. Can you find the rising magma, the freshly formed magma, rising up through the continent? Hopefully you see that on the right. Can you see the deep sea trench? That would be through here, right? That's that deep sea trench. Then we've got lithosphere that includes both the crust and the upper mantle. And we have asthenosphere, which is the lower mantle. A little review.
So why do the two plates not touch each other, and why do they form a deep sea trench?
Well, they do touch each other there, but the deep sea trench basically think of it as the oceanic crust is being pulled down underneath here, and right where it bends, that's where we have the crust is dropping down lower and lower. Meanwhile, the other one is coming towards it, and it does touch it eventually, but it's not immediately at the same level. It's a little further down underwater before they actually touch. That would be at the bottom of the trench where they're touching. The other thing I'd like you to notice in this diagram is a series of volcanoes, these circles, and those, we can measure where those are. We can tell how big they are, we can tell how deep they are, and because of those volcanoes, we can actually figure out exactly where a subduction zone is found. The other thing I like about this is the way it's three-dimensional. And so you can see this whole range of mountains, of volcanic mountains, stretching off into the distance. So we've got different kinds of mountains that are formed. We've got the folded mountains where two continents collide. We have the volcanic mountains, like these ones, from a subduction zone. And then, like ours, we have the fault block mountains, where faults lift up one side of a block of land and drop another one lower. Okay, let's move on to our last boundary, called the transform boundary, which means it moves side to side. Now this one, to show the motion, we have to do more of a three-dimensional drawing, which can be tricky. So I'm gonna draw over this in red so you can see it more easily. And you should draw the same thing that I draw in the same order. If you have trouble doing a 3D drawing like this, just do it with me. So the first thing I'm going to do is this part right here. Then I'm going to go straight off to the side, and I intentionally don't really want it to be a straight line because the rocks that make up the plates are not straight lines either, are they? Then I'm going to draw kind of at an angle back to here and then to there. So now I have one three-dimensional block. And now I'm just going to add the other one. This coming out and this coming out. This one has to be a little higher. It's not quite in line. Then it comes back here. You drop that down there. I'll do that whole thing again a little faster. Now, these are not colliding with one another. These are not separating from one another. They're scraping against one another. And hopefully you can tell from my diagram, the direction of movement is that this one is going to be moving towards us, while this one is moving away from us. Like cars on the freeway. One headed north, one headed south. And really the only thing that we find here, as you can imagine, these blocks of land not being smooth, they get stuck together and the pressure builds up and builds up until finally that pressure is released as an earthquake. And that's really all there is to this one. It's a tricky one to draw, but there's not a lot going on. the way the subduction zone had a lot of things happening, and the diverging boundary had many things happening as well. Okay, so then we're going to write some things down about this type of boundary. Again, I want you to look for three things: features that are found there, the process that it's occurring, and examples. Okay, so convection currents in the mantle, once again, in the asthenosphere, these carry one plate past another. They don't bring them together, nor do they tear them apart. They're just sliding along, going in opposite directions. The edges of the plates stick together until the force builds up enough to break them loose. When they break loose, we experience an earthquake. This can happen with any kind of plate. It could be ocean with ocean, continent with ocean, or ocean with continent. An example is the San Andreas Fault, where the Pacific plate slides alongside the North American plate, causing earthquakes in California. So let's see, features is basically just the earthquake and, I suppose, an earthquake fault. So features would be faults and earthquakes. The process would just be, I guess, earthquakes. We don't really have a name for this process like we do for subduction and seafloor spreading, are the main two. And here's our example. Famous San Andreas Fault. So these were our features. And then the San Andreas is our primary example. Okay, let's look at another video. So this one is going to be like a drone or a plane flying over the San Andreas Fault in Southern California. So here we are flying along, and we can see this crack in the landscape. And if you look to the left and to the right, you could see places where features have been broken apart. All of this kind of ragged zone is where the land has been dragged past itself. I really like this image because you can see it's kind of a scar. I want to pause, dude. Sorry about that. I just can't keep up with how fast it was moving. This is what I was trying to talk about. So we can see where the land is all scarred. On one side of that valley is the Pacific plate. Basically, this side is the Pacific plate, and this side is North America. Pacific and North America over here. And that's the San Andreas Fault in between. Now, one thing that I think is pretty amazing, sometimes when these photos are shown, you can see, for instance, that there is a stream that's coming down from the mountains, and then it hits the fault. And long ago, it was a straight line going to the sea, just exactly what you would expect. But because of the movement on the fault, now the stream comes down, and where it was going is now over here. And so the creek has actually been cut in half, and the water has to flow down the fault line before it can get out to the ocean. Pretty crazy. We can also see man-made features that have been broken apart by the fault if we look in certain places. So for example, if you go to a place in Marin County, north of San Francisco, you can find some fences that have basically been broken apart like this by the fault. But not just this far apart, they're like 20 feet apart. And they were moved all at once during this great San Francisco earthquake of, I think, 1906. 20 feet. Imagine the land moving 20 feet to one side, all within about 30 seconds.
Did anyone die?
Yeah, quite a few people died in that earthquake. Actually, a lot of people also lost their homes, not from the earthquake, but because basically the whole city caught fire as a result of the earthquake. The water pipes broke, they were torn apart by the earthquake, and when a fire started, they couldn't put it out, and it spread from one neighborhood to another. So for San Francisco, it was like a double disaster, the earthquake itself and then the fire. And there's amazing photos you can see. They're over 100 years old now. But like one of my favorite ones, there was a statue of a guy on top of a building, and the earthquake shook the statue off of the building, and he landed in the pavement head first and just dug into the pavement like he was an arrow with his feet sticking up in the air. This big statue of some famous guy. Okay. Now, if we look at this one right here, you don't need to draw this one, but I do want to ask you some questions about it. So, I'm going to do some drawing on it. And I want you to see what you can recognize as we go. What have I just drawn there? What are those red things? I'm going to call on just kind of randomly, and I'm going to start with Marvin. What are those red things I just drew? What do these represent? Deep underground. Marvin?
Are they convection currents?
Perfect. Those are convection currents, yeah. Now, notice right here, and if you were to zoom in, if the sea floor was flat right here, it'd be like that height, huh? But right there, we can see the sea floor is lifted up. And I want you to name that feature for me. Who's next? It looks like Rose. Now, this is not from what we did today. This is from last class. What is that feature right there where the seafloor has been lifted up?
The seafloor spreading.
That is a good answer. That's the process that's occurring there. You're right. Seafloor spreading is occurring here. The seafloor is moving apart. Exactly. So I'm going to move on to the next person. It looks like it's Jessica. Can you name that feature where seafloor spreading occurs? And the hint is that it's higher than the rest of the seafloor. What do you think, Jessica?
I'm not sure.
Okay, well, if you look back at your previous notes, your older diagrams from last class, it would be shown on there. Let's see. Yeah, right here. We get rid of all that stuff. So it's this thing right here. They called it a spreading ridge. But what I'm looking for, I'm not going to use that term. Instead, I'm looking for the mid-ocean ridge. Now, if you don't know that term ridge, basically it means a mountain range. So like a mountain comes up here, and each side of it would be a ridge. There's a ridge, there's another ridge. Then it's going to have another ridge that comes down here. A ridge line is often a good way to hike to the top of the mountain by following the ridge. Let's go back to that other diagram. So that was the mid-ocean ridge. And notice at the top of the mid-ocean ridge, the mountain range is actually split apart here, right? I'm going to ask Jessica, since she passed on that last one, I'm going to ask her to tell me, what is that name of the place where the ridge splits apart? Where the two plates are actually splitting apart. What is that at the top of the mid-ocean ridge? What do we call that? What do you think, Jessica?
Can you repeat it again?
Yeah. So let's look at this diagram. Here's my mid-ocean ridge, right? It's this underwater mountain range that goes off into the distance. And at the top of the mid-ocean ridge, I want to know, what is that thing? It's a split in the top of the mountain. And what do we call that? And by the way, do you guys see how we're practicing for a future test by going over these terms? One good way to get ready for a test is to ask yourself questions like this. Like, look at the diagrams and see if you can label parts of the diagrams for yourself. Because that's what I'm going to have you do on the test, is label these diagrams. So can you go back to that drawing, Jessica, and find out what the name of that thing is? At the top of the mid-ocean ridge?
Is it Rift Valley?
That's exactly right. Perfect. So where the mid-ocean ridge is splitting at the top is called a rift valley. Excellent. All right, let's see, where does that take us to on that diagram that's got a bunch of different types of boundaries at once. So I had the water here, right? And I think we pretty much, oh, one more question. We've been talking about this one right here. We described it as having seafloor spreading. That's the process. We described two features there, the mid-ocean ridge and the Rift Valley. Now, what type of boundary would we call that? And who's next? It looks like Gabe. What kind of boundary do we call this where they're moving apart? The very first diagram we did, what's the name of that boundary? What do you say, Gabe? Are you there?
Yeah, sorry. The audio is being weird there.
Okay. So I'm asking you, what do we call this boundary right here where the two plates are moving apart?
Diverging.
Sorry?
Diverging.
Perfect. This is a diverging boundary, right? They diverge there. Noah, let's continue along with that same idea. And here we have one plate and another plate coming together. What do we call that boundary?
Coming together is convergent.
Yeah, this would be converging, huh? Now, everybody, notice that over here, we're going to have another converging boundary. But this is an ocean floor converging with another ocean floor, isn't it? Okay. Let's see. Let's get rid of this stuff. Let's come back to what's going on right here. What do we call this whole area, this whole region where one plate is pushed underneath another, and that would be for Marisol. Or name the process that's occurring here where one plate goes underneath another.
Converging.
That's the correct type of boundary, yes, where they're coming together. But what is the process where one goes underneath another?
Oh,
We just drew it. Spent a lot of time on it.
Yeah.
One goes under the other. Starts with the root word that means below or under. Look back to the first drawing we did today.
Subduction.
Yes. So the process occurring here where one plate goes under another is called subduction. So we call this place where it occurs, this is the subduction zone. Okay? Good job. And that takes us back to Marvin. And I would like to know, Marvin, what happens to this plate down here? Once it gets pushed really deep, what happens to it down there? So that's for Marvin. Oh, did you answer?
It heats up and then it turns into magma.
Yeah, it heats up, melts, turns into magma. Perfect. Rose. So then we get all this magma down here, and of course it's going to rise up. And what's that going to make when it reaches the surface, Rose?
A volcano?
Yeah, it's going to make a volcano up here, huh? Perfect. Hey, Rose, let me ask you this. What if we're talking about one ocean plate going underneath another? What will happen there? Won't this ocean plate also melt? And then what will it make?
Magma volcano right there.
Yeah, it'll make a volcanic island. In
Yeah.
fact, it'll make a whole row of islands that we call a volcanic island arc, right? Okay, so if you go to look at this assignment, so doing these diagrams was an assignment. I decided I was going to give you points basically for participating in class. So you're going to take photos of your diagrams and upload those. I have also posted this PowerPoint on that assignment, but the PowerPoint has all these diagrams completed, everything labeled, everything drawn. And so if you left something out, you could look at those, or you could use them as a study tool in the future, whatever you might need to help you get ready for the test after the first of the year, right? We don't have any tests this year. Let's look at one more video though. I like this video because it's kind of 3D. It really shows, I think, nicely the way that the magma rises up and moves around in convection currents down in the mantle. So here's the Earth. Look inside there. We can see the magma heating up and rising. Now this is very slow, but here it is at a spreading center, at a mid-ocean ridge with the Rift Valley at the top. And it's pulling those plates apart, and then one plate is getting pulled down underneath another. And so we have this massive convection current under the crust of the Earth, moving the plates around. That's the big idea right there. Nice view of a mid-ocean ridge. Maybe Noah, you asked earlier about the Rift Valley. Excuse me, I didn't mean to say Mid-Ocean Ridge. This is a nice view of a Rift Valley here. And Noah, you were asking about how it's formed and the plates touching and stuff. So look at this video. I think it shows how they're in contact with one another and how the edges of the plate get dragged down deeper to make this really deep part of the ocean floor, the deep sea trench. And then we have magma forming, rising up and erupting in a volcano. All right, so that's all I have for today. That's all I have for this year. So I would like you to take a photo of your diagrams and turn them in. And like I said, this PowerPoint is there for you to use if you need to add to your notes or if you want to use it to study for the test after New Year's. All right, so I hope you guys have a great holiday. Thanks for being here and take care.
Thank you. Have a good one.
All right, see you later.
Thank you.
Bye.
Thank you.
Bye.
Miss you guys. Bye.